Welcome to today's lecture. This will be the last topic we cover, and it will be machine learning. So there's a few things we have to do in order to run our machine learning algorithm, and in this case, we're going to just run a simple regression. But we first need to approach this with the idea that we need data in a certain format. So we're going to go through all those steps. First thing I'm going to do is go ahead and import our libraries. And I'm going to open up this data set. And what we're going to try and do, as you can see here, is predict which company is going to be the most profitable. And so what we're going to do is open it up. And what we see here is a bunch of data. You can see here in the data field information, we have things like firm ID, whether or not it was profitable, the number of analysts covering the firm, number of employees, number of acquisitions, number of independent board directors, a unique ID that the SEC has provided, revenue, what industry code is available, and it seems already there's some missing ones there, different share classes, and whether or not they have paid a dividend. And if we want more information or a little bit more detail, we can go ahead and read through the data description down here. But in general, seems like the data set has what we need in it. I can already tell you we might want to address something with SEC ID a little bit, and we're probably going to need to do something with dividend paid and industry code as well. So let's do a quick describe. Again, remember, this only takes care of the numeric variables. And I should start out by saying we're going to do a little bit of diving into the data and exploratory data analysis, but certainly not a deep dive or anywhere near a large enough analysis to warrant actually going forward with this project. You guys already know how to do exploratory data analysis, so you should do that on your own. What I'm going to do here is just briefly touch on it as we get into the new content, which comes after, and that's the machine learning part. So please don't think that the exploratory data analysis that I am conducting here is anywhere near sufficient for an actual project. Again, this is just to get us to the point where we can run the machine learning models. All right, so describe what we have again is all of our variables. We can see we have some missing. We can see nothing jumps out as a possibly problematic to me at this point. We'll have to see what happens as we go on, but we can go ahead and dive into some more information. So we're going to see if there's any variables we can drop right away because they contain no information. And what I mean by that is there a variable that has so many, or is a unique variable to every observation, or just has a large number of values that it's not really going to be beneficial? And we'll talk through that as we see an example here. So this for loop is just going to loop through each of the columns. It's going to print the column name. It's going to print how many unique values there are in that column, and then it's just going to have a little divider. So if we run this, firm ID has 891 unique values. Probably don't need that. We'll address it later. SEC ID has quite a few. Revenue has quite a few. Industry code has quite a few. What I'm going to choose to do at this point is drop firm ID. First of all, this should be the easiest one because there are 891 observations that have unique values. In other words, this isn't going to tell us anything. It's essentially just a different value for every company. The other one that has that 891, which you notice I did not include, is revenue. And the reason I'm not including revenue is dropping it because it is a continuous variable. They should have different values, right? If we're in the millions or hundreds or even thousands, whatever dollars, depending on the units we have, because it is continuous, every company is likely to have a slightly different answer. So we don't want to get rid of this. SEC ID, I'm also choosing to drop. It's not unique to every company, and we could make the argument that we do want to keep it. I'm just choosing to drop it. Again, we could explore it with and without and see if it actually adds anything to our analysis. But at this point, I'm choosing to drop those. So we're going to drop firm ID and SEC. And now we are left with an updated data set where we have a few less observations. You guys should be familiar with this general plot. It's going to be a box plot and a distribution plot, and we're going to go ahead and loop through all of the different numeric variables in that data set, plotting them out. And I'm going to actually come down here and expand this to start. And we can kind of just scroll through what we have. So here's profitability. Yeah, it makes sense. It's a 1 or 0. Number of analysts. This makes sense. You either have 1, 2, or 3, it looks like. Number of employees, yeah, there's a large number here. This one observation, maybe it's an outlier, but I'm going to go ahead and assume it's not at this point because there are, some points that are leading up to that. It's not that this is, hundreds and hundreds of values above the next closest. Number of acquisitions, so possibly something to be concerned with. We can decide what we want to do, but again, there are other points leading up to it, and you can see 8, and the next closest one appears to maybe 5. So, probably not that big of a deal. Independent board directors, that's perfect. Revenue. So there is one company that has a significantly higher revenue than every other. We may look into that. It's about double the next closest. So as I mentioned here, one firm does have significantly higher revenue. It's a possible outlier. Some other things, right? Some other things that you may have taken in, not necessarily from the visualizations, but possibly from the fact that I did a dot describe above. I don't know if you caught this, but we do have number of employees less than 1 for a value, and we'll look at that in a minute. But let's first look at revenue. So we have 3 observations, 3 firms that have revenue above 500. Because it's not just one value, because there's nothing at this point to indicate that these are errors in the data, I'm going to choose to retain these 3. What you choose to do in a situation like this would be up to you. I might want to dive into the other observations associated with these 3 companies and see if they're also outliers or if they're consistent. Continuing on, what we have here is number of employees. So what we can do is do dot describe. We could have done min, we could have done any number of things, but this is the issue I addressed above. Notice here, minimum value is 0.42. Well, we can't have less than 1 employee. So we're going to go ahead and correct this. What I'm going to do is just replace any values that are less than 1, and I'm going to replace them with a value of 1. So number of employees, I'm just going to set it equal np.where. So any place that the number of employees is less than 1, I'm going to replace it with the value of 1. And if the value is greater than 1, then we're just going to keep the number of employees that are already listed there. So if we run this cell, and if we want to come back up here and run the one above again, notice that our minimum is now 1. So now we have to address filling in missing values. And there's a bunch of ways of doing that. I'm going to just come up with a couple here and talk about them. But here's our info. For instance, we need to fill in number of employees. We may or may not choose to fill in industry code. That's on us. We can do what we want. And it looks like we have a couple for share class. So not a whole lot, but let's go ahead and first address industry code. So I'm going to go ahead and actually create something, and I'm going to create it this way on purpose. I'm going to write the word missing 9999. So anytime there's a missing industry code, we're going to fill a missing 9999. And if you recall, I can just show us here profit head. If you read up above the description of industry code, it's going to contain a letter followed by a number that contains the industry and the sub-industry. So we want to kind of keep these separate. We want to make sure that our observations have a letter and a number component, which is what they do here. And what I'm doing here is I'm actually going to strip out the numbers and the letters. Okay, so I'm going to right here say, go to industry code. And this is going to be our first time actually working with strings. So I'm going to show you just some very basic stuff. And this says .str.replace. So we are going to utilize this string replacement method. And in parentheses, what we're going to do is put what we're looking for. And this is called a regular expression. In these brackets, what you see is a caret followed by a lowercase a dash lowercase z, uppercase a dash uppercase z. What this is saying is anytime there is a letter, whether it be lowercase or uppercase, A through Z, we're going to replace it. What we're going to replace it with, well, notice here after the comma, I just have 2 quotes with nothing in between, which means we're just going to replace it with nothing, essentially deleting it. And that is going to be our industry, right? So anything that is a number, because it says if it is not a letter, what are we going to do? The caret says not. So anything that is not a letter, replace it with missing. So our industry is just going to, in this case, find the 8 and the 5. They're not letters. We're going to replace them with missing. We're going to be left with a C. Sub-industry says anything that is a letter, replace it with missing or nothing. Remember, there's no caret in this one. So it's going to go through and find any letter and replace it with that. And then it will be the sub-industry. We're going to drop that original column, and I'm going to print out the head so we can see it. And what you see is we've created industry. Where is missing? The word missing shows up. Where sub-industry is missing, it's 9999. Industry has a C and an 85, a C and a 123, and so on. So we have now created two new variables. We've created some new features for our analysis. Same thing with share class. What I'm going to do is anytime share class is missing, I'm actually going to fill it with the word missing. The reason why is when we create dummy variables later on for analysis, I want to create a dummy variable for share class S. I want to create a dummy variable for share class C. I'm also going to create a dummy variable for share class missing. So all those missing ones will be treated like they are their own share class. So at this point, everything's fixed except for number of employees, and that is a continuous variable. So I don't want to fill it in with just some random word or anything like that. I'm going to actually go ahead and create or fill these in on their own. And I want to address something. Above, I have filled things in with constants. I'm not choosing to fill in number of employees yet. In machine learning, we have this concern that we are going to have data leakage or information leakage. When we create models, what we need to do is, as you see below, we're going to create a training data set and a testing data set. What this means is the training data set is the data we're going to use to train a model. Okay, it's going to see this data, it's going to learn from this data, and it's going to train and learn to make a prediction. The testing data is data that is not part of that training process. It's held out. It's unique and independent data that once our model is fully completed on, we can use this testing data and we can test how well our model does on out of sample data, data that it hasn't seen yet. The key here is that the data and information from training does not infect what we have in testing. They need to be fully independent, unconnected. So if we are going to fill in, let's say, number of employees with the average number of employees for a firm in our sample, well, if we do that before we split our data into training and testing data, and we calculate the average number of employees over the entire sample, the full data set, and then fill that in, that's going to result in data leakage, because if we take 20% of our data and hold that to the side as testing, and we keep 80% of our data and use that for training, right now they're separate. But if before we made this split, we calculated the average of the entire 100% of the data set, well, now we're including some information that's in the testing data and the training data, because we're calculating the average of that whole data set, which includes those observations from training and from testing. So the way we can avoid this is by creating our training and testing data. And then after that, we can go ahead and make this calculation to fill in the average number of employees. Now, the reason we were able to fill in these other values ahead of time is, notice, this is a constant. We're filling these in with a constant. It doesn't matter. We're not calculating the average of anything. We're not taking information from testing data set and the training data set or anything like that. We are literally just making the rule to fill in any missing value with the word missing 9999. There's no calculation. There's no input from any data to calculate this value. It is a constant value that we're filling in. So it doesn't actually result in any issues. But because this other one for number of employees is going to be calculated based on the data going into it, we actually have to do that after. And you'll see that come into play here in just a moment. All right, so here what we're going to do is import from sklearn.model selection train test split. And this is what I was talking about. We can actually go ahead and, rather than breaking up our data on our own, allow Python to do that for us. So I'm going to make an X data frame and a Y data frame. It's going to take our data set, profits, and I'm going to drop our variable of interest. In other words, remember, we're trying to predict which company is profitable. So I'm going to drop that. And these are going to be all of our explanatory variables. Our target variable is now going to be only that profitable variable. So what I've done at this point is I've just made two data sets, X, which contains all of our explanatory data variables, and Y, which contains only our target data. What we're going to see next is we're going to say train test split. We're going to call X data frame and Y data frame. We're going to say test size equals, and I put 20% or 0.2, and random state equals any number you want. I just put 1, 2, 3, and we'll talk about what this is doing. So what this is doing is going to take the X data frame and the Y data frame, and it's going to randomly select 20% of that data. 20% of that data is going to be saved to the testing data sets. 80% of that data is going to be saved to the training data sets. So we're going to train on 80% of our sample, and we're going to test it on the remaining 20%. Random state equals 1, 2, 3 just allows us to repeat this analysis with the same numbers. So if we don't set a random state, like I mentioned already, it's going to randomly select 20% and 80%. So every time we run this, the sample, how this is broken up, is going to be different. So our results will never be the exact same. However, by setting a random state in this argument here, it now ensures that every time we run this, it will be the same randomly selected 20% because we have a starting point. So if we run this, all this does is it confirms the shape of our training data and our testing data. And you notice here, training data has 712 observations, and there are 712 target variables or outcomes to those. There's 179 observations in our testing data and 179 target variables. So it looks like our data is set up correctly. We want X data sets and Y data sets to be set up this way. All right, so now we can go ahead and address the missing values. So I'm going to simply say, let's fill in the number of employees that are missing with the average value. So keep in mind here, I'm calculating the average on the training data only and saving it to mean value. And in fact, we can just see what this looks like. Let me print this out, mean val. So it's 29.8. Right, so 29.8 is that mean value. So now what I'm doing is I'm saying take the training data, number of employees, and fill it in with that mean value. Right, fill it in with the mean value 29.8. Notice I'm also using that exact same mean value to fill in missing values in the testing data set. So we'll run this first of all, and we'll see that everything's been filled in. We're perfect. Training is full. Testing will also be full. But let's talk about why I calculated the mean value only in training. So the reason I do the mean value only in training and use that to fill in the mean values in both training and testing is because what do you do when you get a data observation passed off to you? And it's only one observation, and they want you to predict, is this company going to be profitable? Well, what do you do if it doesn't have the number of employees there? You can't calculate the mean value of a single observation. So what we do is we calculate the mean value of the training data, and we use that in the testing data set. Whether we have 179 observations in testing, or it's a new company coming in to be put through the model and it's a single observation, we know exactly what value is going to go into missing number of employee observations. All right. So here's what we have. Our data is getting closer to being ready. The next couple of things we need to do is create dummy variables. In other words, we can't pass letters or strings into our analysis. We need to convert share class into numbers. We need to create numbers for dividend paid, industry, sub-industry, and so on. So we're going to import one hot encoder from the feature engine library. And I'm going to pass in all those variables that need to have dummy variables. Share class, clearly that's a character. Dividend paid is a character. Industry is a character. And notice sub-industry. Even though it looks like it's numbers, it actually is an object. For instance, we can look right here. 10 space 1, 2 is not a number. And that's fine. These numbers aren't actually meaning anything. They're just ways to classify something as a different sub-industry. So for instance, I don't know, maybe 18 means natural gas and maybe 10 space 12 means technology or computers or who knows what they mean, but they don't represent the number 18. They represent some classification. So we're going to go ahead and do that. Drop last equals true, ignore format equals true, and that's just going to allow us to create dummy variables for any format of variable in there. And what you're going to see here, OEC is what I've called this. So we're saving off all these rules for the one hot encoder, or think of it as the dummy variable creator. We're saving them into this object called OEC. OEC dot fit transform. What this is going to do is it's going to transform or fit and transform. In other words, it's going to go through share class and determine how many unique columns we need. So let's say there's only 3, right? Actually, let's do this with dividend paid because that's easier. There's either a yes, a no, and nothing else because it had no missing values. So it's going to go through and it's going to determine that there are 2 values in dividend paid, yes or no. It's going to then make 2 columns for that. One column is going to be dividend paid yes, one will be dividend paid no. Any place that dividend paid has the word yes, well, dividend paid yes column is going to take a value of 1. Any place it's no is going to be a 0. And then for dividend paid no column, it's going to do the opposite. Anytime it says yes, it's going to place a 0 there. Anytime it says no, it's going to place a 1. Now, because we have this argument drop last equals true, turns out we don't actually need that last observation. So dividend paid no is actually going to be dropped. And again, the reason why is if there's only 2 outcomes from dividend paid, yes or no, if I tell you only the results for the dividend yes column, by default, you're going to know if the dividend was paid no, right? Anytime this says a 1 for the value of yes, we know it was paid. Anytime there's a 0, well, we know dividend paid no would have been a value of 1. So we actually only need 1 less value than is present. So we're going to fit and transform that, creating those new variables. Now, we're only going to transform the test set. And what this means is we're not going to recalculate all of these share classes. So let's go to dividend paid again. And in this training data set, there's yeses and nos. So we know we're going to have a column for that. Okay. In this, let's say there's for share class, there's C's, Q's, and missing. So we know they're going to have 3 share classes for that. For industry, I have no idea how many are. Let's say there's 10. We're going to have, 9, 10 minus 1, drop that last columns for this. Now, the reason we don't refit this on the testing data is let's go to share class because I know there's at least 3 columns for this, right? There's C's, there's Q's, and we know we filled in missings. So we know by drop last, we're going to have 2 columns if we assume there's just those 3 values. We're going to have a column for C's, a column for Q's, and we're dropping the column for missing. Now, what if we get in the data set for testing and there's only, a C in there? They're all C's. There's no Q's, there's no missings. Well, we can't refit this because then what if later on we get a value of missing? Or what if we get a value that is a Q and it hasn't been seen yet? Well, we need to ensure that regardless of what observation comes in, that the same columns are there, right? If we went and fit this again and there was only a C, well, now we're going to only have 1 column. And that 1 column is going to be dropped because it's dropping the last. Or let's say we only get C's and Q's in testing and there's no missing value. Well, now in this testing data set, we would only have share class C, it would drop Q, and missing would never even be in there. So the models wouldn't match. We would have a training model which has a missing column, and we would have a testing data set that doesn't have missing because the data is different. So we want to ensure that these are the exact same. And by doing that as just transform rather than fit transform, we actually are able to accomplish it. So here we go. Training data, perfect. It's done. We'll run it. Here's what we get. We have the continuous variables we've already looked at. We've got share class C and Q, and apparently there's an S as well, and then missing is dropped. We've got dividend paid yes, dividend paid no was dropped. We've got all of these industries and sub-industries, and whether or not we choose to actually keep them all, it's kind of up to us. Turns out we now have 112 unique columns because there are a lot of industries and sub-industries. And again, we might say, hey, sub-industry there's just too many of them. It's not worth keeping that variable anymore. Well, we can drop those if we choose, but that's up to us to do. But what is important is that now we have two sets of data which are ready to go into our model. We've cleaned them, we've gotten rid of missing values, we've ensured everything is in the same format, we've ensured that we only have numerical variables, and they do in fact match 5 by 12, 5 by 12. All right, obviously the 5 is just from the head, but 112 columns is what's important here. Okay, so we are going to stick with a logistic regression here. It's a very simple machine learning model. We're going to predict something. We're going to, again, set up random state, and we're going to set max iterations to 10,000. It's going to take 10,000 iterations through this to see if we can come to the correct solution. So we're going to set this up as LR. You can change whatever you want. I'm calling it LR for logistic regression. We're going to say LR.fit. We're going to fit it on the training or the X training and the Y training data. So in other words, it's going to take all of the X data. It's going to use this to try and understand how it got to the Y or target variable. So once it's been fit, what we're going to do is we're going to say LR, which is going to store all of that model information, .predict on X test. So now we've fit it on that training data, right? We fit our logistic regression here. And now we're going to say, okay, pass in these exact same variables with unique values, right? All these observations in the X test data set, pass those in. Use this trained model to say, okay, is observation 1 in the test data set going to be profitable or not, 1 or 0? Observation 2, 3, 4, and so on. And we're going to save those under Y predict LR for logistic regression. We're going to save that. So we could print that out. In fact, I can show you what it looks like. Y predict LR. There it is. Here's the predictions, 1s and 0s. Not terribly helpful at this point, but we're actually going to create this little function here, draw CM for confusion matrix. We're going to pass in 2 arguments, the actual values, so the Y test values, the actual outcomes, and then our predicted values. And what it's going to do is draw a confusion matrix. We've imported it right up here. It's a built-in function with those values. Now we're going to have this confusion matrix. And then all these steps down here are going to do is just format it nicely so we can very clearly and easily see what's going on. And we'll talk through these results. All right, so it's been created. We're going to print out some spacings. We're going to print out the training accuracy, testing accuracy, and then our confusion matrix. So what are these, first off, before we print it, what are the LR.score arguments? Well, it's telling you what is the accuracy of our model? How accurate were we in predicting 1s and 0s on the training data? How accurate were we predicting 1s and 0s on the testing data? And then this is our testing results. So let's talk through everything that's printed out. What we have is training accuracy. We predicted about 82% of these correctly during training. During testing, we predicted about 82% of these correctly. That's fantastic. First, let's talk about that before we even get into the confusion matrix. The goal in machine learning is obviously to have a high accuracy or high measure of performance, whatever it is we're looking at. But it's also equally important to have training and testing performance that is similar. You will notice later on in your data science career that there are certain models that will fit really, really well on the training data if you don't do anything to them. They'll essentially learn what every single observation is, and you'll probably, get 99, 100% accuracy if you don't do anything. Then on testing, you might only get 80%. You might say, well, this is still pretty good, right? We got 100% on training. Well, that's actually very bad. The idea is you want to create a model that does not overfit on the training data. It does not learn every in and out of that training data because that model is not generalizable to out of sample data. A model like this, where we get the same performance on a model or on the data that it's trained on as we do on unseen, new, unique data, is actually a really good model because it tells us that it doesn't just perform well on one set of data, it actually seems to be performing well on multiple sets of data. And now getting down here to the confusion matrix, here's our predicted values of 0 and 1. Here's our observed values of 0 and 1. So you can see, how did we do on a predicted 0? Well, we predicted 0, and it was actually 0 95 times. We got it incorrect 13 times. Well, we predicted 1 and got it correct 52 times and got it incorrect 19 times. So you can see how the model's done. We know we got about 82% accuracy. Now you can actually see where and what type of predictions it did well in. All right, so now we are going to look at feature importance. So I'm just going to get the column names from our training data. It doesn't matter. I'm going to say, let's go into our logistic regression and get the coefficients. And I'm going to round those to 2 decimals. And then I'm going to actually get the absolute coefficients as well. And I'm just going to print those out. And what you can see here is we have, was a dividend paid? Yes, that appears to be the very important coefficient, most important by quite a bit. Number of analysts covered, you can see it's a negative 0.81, but the absolute value of it, the magnitude of it, is pretty high. So it is also an important coefficient. These different sub-industries seem to be important. I'm not necessarily sure what all these are, right? They're just different classifications. We would, in the real world, we'd look up what is sub-industry 23 or 46 or industry E and so on. But the idea here is now we know when you pay a dividend, you are more likely, the coefficient, you are more likely to be profitable. The more analysts you have covering you, the less likely you are to be profitable, and so on. Next up, we want to look at this idea of cross-validation. And it's common to do 5-fold cross-validation. And what is happening here is essentially what we're doing in cross-validation. So if we take our training data set and we train on it and it learns it, and it might learn that particular data set well or not well, but it is only doing that on one data set. We want to ensure that we are not having an instance where it is just unique to this one data set. And one way we're doing that is, we've already seen above, we have the testing data, which we hold out. But another great method is cross-validation. So what's happening here is, you can imagine what I have highlighted is our entire training data, right? I've just broken it up into chunks of, let's say, 20%. So there's 5 of them. Well, above what we did is we trained on this entire bit of data. What we're doing now is, with cross-validation, we're saying, okay, here's our training data. We've broken that up into 5 unique chunks. Let's now train on all of these, which I've filled in with X's, and tested on this group. Now what we're going to do is move that testing group to 1 over. We're going to use these 4 groups with X's to train and test on this group. We're going to train on the X's and test on this group, and then this group, and then this group. So now what we've done is we've turned that training data into 5 unique sets of data rather than just 1, to ensure that it is a robust model, a model that performs well across all different types of data. So we're going to import a new library, cross-val score, right? And what we're going to do is set up our model again. We don't have to, it's above, but I'm resetting it up. This time I'm calling it model. You can call it whatever you want. I'm going to call cross-val score, which is what we just brought in. I'm going to pass in the model, the X data, the Y data, and how many of these iterations we want. So this is for 5. Imagine if we put in 10, you would just have 10 of these little sections of data, or 7 or 2 or whatever you want. So I've got 5, so it matches our visualization above. And scoring equals accuracy. There are other types of scores. You may learn or want to use them in unique situations. We'll talk a little bit about scoring later on. And I'm going to print out the individual scores for all 5 of them are, and I'm going to print out all the scores. I'm going to then print out the average score and the standard deviation of the scores. So there we go. This time, what we got is 77%, 79%, 80, 77, and 80. The average score we got was 79%, and the standard deviation was 1.2%. So you can see here, now we have a much broader view of how this performs across different data sets. Okay, so continuing on, we want to talk about grid search. So in machine learning, there are these things called hyperparameters, and they allow you to fine-tune your models. Now, granted, logistic regression doesn't have a ton of ability to be fine-tuned, but there are a few arguments. And if you want to read about them, you can simply Google hyperparameters logistic regression, and a couple of those that go into it are C and solver. You're going to have different models. Let's say a decision tree. You're going to have things you can do. You can do things for a random forest. You can do things for k nearest neighbors. You can do hyperparameter tuning for any type of machine learning algorithm you're looking at. But what this is allowing us to do is to fine tune or change a couple of things that are going into this model behind the scenes. Okay. We can then look at the results across all of these different combinations of hyperparameters and see which one performs the best so that we can then fine tune the model to get the best performance possible. So again, here's our base model, just setting it up again, same as above. We're going to use this grid search library now, grid search CV. We're going to pass in the base model. The new argument is param_grid. And what you can see is we pass in the parameters, and there is a dictionary format to this. It needs to be in this format because this is what is accepted. And now what we have is a dictionary which has C values of 0.5, 1, and 1.5, and solver of LBFGS and liblinear. And again, you want to know what parameters can be tuned in a logistic regression or any machine learning algorithm for that matter. Simply Google what that model is that you're using, in this case, logistic regression, and then hyperparameters, and it will take you to all of those available ones. So we're going to fit it. We're going to fit this model on our data, and it's going to tell us what are the best params. The best parameters, I'm going to print that out. And I'm going to print out the tuned model, right? That is going to be our best model, best score. So let's go through. It's going to take a minute because it's actually running quite a few models. There you go. Of those, the best model that we could produce is with a C of 0.5 and a solver of liblinear. And in this case, what we have is training performance of 79.6%. Now we can save this model. We're going to save it off as a model. Best model is going to be our tuned model.best estimator. And that's going to save the model as best model. We're going to print it out. And then we're going to go ahead and print out our performance. All right. So it's telling us right here, logistic regression. Here is our C value, max iterations, random state, and solver. Again, 0.5 matches 0.5. Liblinear is the solver method. And then I'm going to say print out something here with 3 decimals. Well, what is it? It's going to be the best model. Remember, this is the model we've saved. It is the model that we are happiest with. Dot score, same as above. We're going to take our model dot score and we're going to pass in an X test and a Y test. And what we're finding is this model produces performance of 82.7%. Okay, so let's talk about some performance measures. We've already looked at a confusion matrix, but what's actually going into that confusion matrix is what you see here. I've just got the labels a little bit different in where they're located, but the idea is if you predicted a negative and it was actually a negative, you have a true negative. If you've predicted a negative and it's actually a positive, you have a false negative prediction. If you predicted positive and it's actually negative, you have a false positive prediction. And if you predict positive and it's actually positive, you have a true positive prediction. And this gets to these 4 measures of performance: accuracy, precision, recall, and F1 score. Accuracy simply captures the fraction of predictions our model got correct. It's a very broad measure. In contrast, we have precision and recall. Precision is a measure, it talks about how precise or accurate a model is. out of those predicted positive, how many are actually positive? And think about it, this is a measure is good when the costs of false positive classifications are high, example being email spam. Okay. In other words, a false positive, if we're trying to predict email spam, it's pretty costly if we predict something as spam if it's not. Imagine you're getting a bill from your mortgage and we accidentally classify that as spam. It goes to your spam folder and you never see it. That's a very costly mistake. Okay. So if this is the environment you are in, maybe instead of using accuracy, overall accuracy of your model, we care more about making sure we do well with true positives. Flip side, recall, right? It's a measure best used when there's a high cost associated with false negatives. In other words, fraud detection. If a fraud transaction, a true positive, is predicted as not fraud, well, that's pretty bad for the bank. That could be very costly. And here's the formulas for all of these. TP, true positive, over true positive plus false positive, or true positive over true positive plus false negative. And then F1 score is just going to be a measure which is trying to seek balance between precision and recall. So at this point, accuracy is probably in general going to be the most common measure you would use, though there will be maybe some instances where you might think precision or recall are a good alternative. Very rarely do I personally use F1 scores, but the case comes up where you want one, you now at least know how to calculate that. All right, so from sklearn, we're going to import a few different things: classification reports, confusion matrix, and the ROC curve. What we're going to do is we're going to take our best model and we're going to predict values. So the model we trained above, right, that best fitting one, we're going to predict values for X test. We're going to save those out. We're going to get the classification report and the confusion matrix and show you what these look like. Okay, so remember above we had that nicely colored and formatted confusion matrix? Well, the reason we did that, the reason we made the extra steps to create our own function is this is what a confusion matrix looks like if you just call it directly from the sklearn library. Right, bare bones minimum, not that helpful. Numbers match, like numbers are what they are. When we look below, we'll have, if you were to run your custom confusion matrix function, you'd notice the numbers do match. But our measure or our output looks a lot nicer and it's easier to read. What this classification report is reporting is right up here above. This is presenting us with precision, recall, and F1 score, as well as accuracy. Right, so here we're getting all those measures that we discussed above, and we can go ahead and get them right here, easily accessible. You could also calculate them yourself with the information right here, but we're able to get that again right up here. So let's display the confusion matrix as formatted above, just to illustrate this point to you. Right, so here we have the performance, 82.68%. Here's the accuracy again, it matches, only difference being this one is rounded. Notice here we've got 99 and 15, 99 and 15, 1649. So these results that we have down here do in fact match up here. We're just formatting things a little bit nicer so you understand why this is happening, right? This is a lot easier to read and understand than this. Okay, so let's talk about the ROC curve that I imported, and I'm importing it again here by mistake. You don't need to, again, I just did it. So let's go ahead and predict probabilities. So what's happening behind the scenes in this logistic regression? Well, it is coming up with a probability for each of those X variables, right? So it's going through, it's saying, here's the probability that it's a 1. And if it's above 0.5, it's classifying it as a 1. If it's below 0.5, it's classifying it as a 0. Okay, that's what's happening. So let's actually comment out some of this really quickly and run this. Here's the actual behind the scenes probabilities that are going on. Remember above when I printed out the predictions, they were a bunch of ones and zeros. Well, this is really what's being predicted. Here's a 1, here's a 0, here's a 1, here's a 0, here's a 0, here's a 0, here's a 1. And I'm saying this based on whether or not it is greater than or equal to 0.5. All right, so let's know that that's what the y hat is predicting. So if we don't say predict, we say predict proba is predicting the probabilities. So what we're going to do is utilize this ROC curve. We're going to pass in the y tests and then the y hat or the y predictions. And we're going to utilize this to create this figure that I'm going to show you now. So this dotted blue line would be a random choice, 50-50. You are going to randomly select ones or zeros. This is what our model is providing us. Okay. The best point would be right up here in the top left, right? 100% true positive rate. What this tells us is how well this model does. We want it to be, again, as far top left as possible. So it's not doing bad. And we already knew it wasn't doing that bad because we have a value of 0.83 or so. So that's relatively good performance. But this is a visualization. We can go ahead and do this based on the predictions that we have. Now, let's go ahead and utilize that information that I showed you above. Utilize the information that I said we're basing our predictions on 0.5. And, well, what if, is it possible to do better than what we've accomplished if we don't use 0.5, right? What if instead I said, let's say every firm with a probability greater than 40% is profitable, or maybe greater than 70%? Or is there some point where we can actually improve this model by adjusting that threshold value? So we're going to go ahead, get our best model again, same model we've been using. It's already the trained one. We're going to predict probabilities. I'm going to save this as y test probs because these are the predicted probabilities for our outcomes. I'm going to then just make a copy of it as a data frame. And what I'm doing down here is I'm going to make a new prediction. So we already have a prediction. It's those predictions that we've already discussed relative to 0.5. Our new prediction is going to say anytime that the probability is greater than or equal to the threshold, in that case, it's this 0.5. We're setting it up like this so we can change this. Well, it's going to be a true value, and we know trues take on a value of 1, so it's going to be a 1. Okay. And this is going to be our new data set. So rather than using our y hat or our y predictions, we're going to use the predictions that we're creating, right? We're now only going to keep that new prediction, which is going to be a 1 or a 0 based on this threshold that we're defining. Now we're going to run that classification report again and the confusion matrix. Now notice this matches exactly above because I have set our threshold to 0.5. We know that is the default threshold. But watch what happens when I change this to 0.4. Right, we've got 99, 15, 16, and 49. Now we have 90, 24, 12, and 53. Let's go to the extreme, 0.1. Now we've got 16, 98, 2, and 63. Let's go to the other extreme, 99. Right, everything's been classified in the one group. Let's put this back to 0.5, run it how it was. So it's tough. It's kind of difficult, right? We can't just go through and manually type in some random numbers and hope we visually see which one's best. So what can we do? Well, the last thing we're going to do is write a for loop, combining everything we've done so far in the class, combining our ability to loop through data, combining our ability to understand that different thresholds could have different performance, to understanding that we can get probabilities and make predictions from that, and then assess our performance across all these different levels to determine which model is best. So for I in np.a range, and this is going to be just a range of numbers, I'm running these from 0.1 to 0.9, and the steps are going to be at 0.1. So in other words, think of it like this: 0.1, 0.2, 0.3, 0.8, 0.9, and so on. So that's what it's doing. So for each of these values, all right, we're going to set the threshold equal to that. So the threshold will be 0.1, then 0.2, and so on. Notice what we're doing below. This is the same as above. We're going to predict the probabilities. We're going to keep those probabilities. And now we're going to make a new prediction where we say if the predicted probability is greater than or equal to the word threshold. Exact same as above, except this time threshold is going to be dynamically changing. Now we're going to keep just that observation, just that prediction. We're going to then go ahead and print out threshold level so we know what the results correspond to. Threshold level of, in this case, 0.2, point whatever. Then we're going to print out our confusion matrix and our classification report. And when we run this, we can come down here and see, we can just focus on accuracy. If we want, we can get the other details later. You could even replace this confusion matrix with the confusion matrix that we've made that is easier to read if you wanted. But you can see here at 10% threshold, 44% accuracy, 74%, 80%, 80% at 83%, 83% at 60, 80% at 70, 78% at 80, and so on. So maybe we know that it's between 5 and 6. So let's say, let's start at 0.5 and let's do 0.65 and let's do at 0.05. All right, so now we're going to drill down and see if maybe we can get some better insights. So we're 82, 83, 83, 83. So it seems like, right now it looks like we're probably going to get to about 83%, which is perfectly fine. Notice that the way we get to 83% actually is a little bit different. These models actually don't perform the exact same, even though performance percent accuracy is the same. But you could keep diving down deeper and deeper, or you could try things like, what if I change some other hyperparameters by going out and looking at that? Or if you want to on your own and you're interested, go out and look at how would it perform if I used a decision tree, or how would it perform if I used a random forest could actually make this performance better, or better yet, simply doing something that you already have the skills to do. How could I improve performance if I went out and I made some new features, right? We've made features. We made industry and sub-industry. Those are new features. Well, what if you made some new features from the data? What if you combined some things? What if you thought about ways to extract new information from the data? Adding those features could, in fact, help us with our performance as well. So that will do it for the introduction to machine learning. You guys are good to go on the last assignment, and I thank you for the class. It's been a blast.